In this video, we'll take a look at the Diels-Alder reaction. So first, let's define what the Diels-Alder reaction consists of. Well, it's a pericyclic 4+2 cycloaddition. So first thing we'll do is define each of these terms because they aren't something we've used before. So pericyclic simply means that a pericyclic reaction rather involves a transition state that has a cyclic geometry. So just meaning a cyclopentane or cyclohexane, something along those lines, that transition state has this cyclic geometry where there's a continuous chain of carbons that are in a shape. And additionally, this forms in concert. So it's a concerted mechanism in which bonds are forming and breaking simultaneously. This is a similar type of mechanism to what's involved in SN2 and E2, where you have this concerted mechanism which bonds are being formed and broken at the same time. That is a key feature of pericyclic reactions, and the Diels-Alder is a pericyclic reaction. Then, next thing to talk about is the 4+2. So this refers to the number of pi electrons involved in the reaction from each reactant. So 4+2 by definition has two reactants, which are usually two different molecules, but it could be two different regions in the same molecule that has this feature where you have 4 electrons that can come from one area, usually one molecule, but it could be a specific area of one molecule that reacts with another area or another molecule that consists of 2 electrons. So this is a bit arbitrary and hard to understand without an example, but we'll get into it. But simply what you need to take away is there's 4 pi electrons from one region and 2 pi electrons from another region, and that's what's reacting in the Diels-Alder. And then lastly, this is a cycloaddition, which means that you have a cyclic product that is formed, and it's usually formed from 2 or more areas of unsaturation. And again, this is what I'm referring to with the 4+2. So these 2 areas of unsaturation, one area has 4 pi bonds, or 4 pi electrons, and the other area has 2 pi electrons for a total of 6 involved in the reaction. And again, these are usually 2 different molecules, but they can be 2 different regions in the same molecule, which is why I say 2 or more areas of unsaturation. All right, now a little bit more details of the Diels-Alder specifically. So the cycloaddition product for the Diels-Alder is always a cyclohexene. It can be bicyclic, but at least one of the cyclic structures is going to be a cyclohexene. You're always going to form the 6-membered ring with one double bond involved in that product formation. And additionally, the Diels-Alder consists of a diene and a dienophile in the reaction. And the diene contributes the 4 pi electrons that we were talking about in our 4+2, and the dienophile contributes 2 pi electrons. Now, a diene is simply a molecule that has 2 alkenes or 2 pi bonds, and that's why each of those double bonds consists of 2 pi electrons to give you the 4 total pi electrons. And then the dienophile is 1 alkene, 1 pi bond that is contributes those 2 pi electrons. And remember, dienophile means diene loving, so that's why we have diene and dienophile, is that because that is exactly what's interacting, is the diene with the dienophile. And here was the traditional, or the very first Diels-Alder reaction that was discovered, and you have this dienophile 1,3-butadiene, which is just this diene here, which has these 2 pi bonds, and then the dienophile here is just ethene. They react together to form this cyclohexene product. Again, this is always one of the products of the Diels-Alder, is this cyclohexene moiety. Now, this particular reaction isn't very fast, so it was done under high temperature and it was allowed to react for a long time, and the yield wasn't very good. So they tried to understand more of the mechanism to understand how to make this reaction more efficient and go faster. And what was found is that the Diels-Alder is promoted, so it occurs more quickly if you have an electron-rich diene and an electron-poor dienophile. So here is our dienophile then, and we're adding to it electron withdrawing substituents. So we're making it more electron poor. So that's the difference here between ethene and this cyanoethene. The cyano group has a very strong pull of the electron density away from the alkene, making this region much more electron poor because of the electron withdrawing nature of this group. And if you add more electron withdrawing groups, like another cyano, that will further increase the reactivity. And then if you look at the diene, we are adding a methyl group, which is somewhat electron donating through hyperconjugation. And then if you add like a methoxy group that has the lone pair on the oxygen, that can resonate in and give you a electron donating nature through resonance, that is much more electron donating. So again, this makes this electron rich diene. So this pair increases the reactivity towards this Diels-Alder cycloaddition type mechanism when you have an electron poor dienophile and an electron rich diene. All right, for the remainder of the video, we will look at a few questions to illustrate how the Diels-Alder actually works and how we can predict the products. So that is simply our question here. Predict the product for the following reaction. And since this video is Diels-Alder, we know these are all going to be Diels-Alder reactions, but if this was in a mix of reactions where you're unclear what type of reaction would undergo, you need to be able to point out a few characteristics that makes it clear which pathway is necessary. So here it's clear that it's Diels-Alder because you have a diene here, which again is simply you have two alkenes in one molecule, and then you have a dienophile here, which has one alkene, and to top it off, this is electron poor. It's an electron poor dienophile because we have electron withdrawing groups in the aldehyde. That is pulling the electrons away from the alkene to stabilize the partial positive charge on the carbonyl rather. And in essence, that pulls the electrons away from the alkene, making it electron poor. And then again, through hyperconjugation, the diene is electron rich because of the donating ability through hyperconjugation of the methyl groups to the alkenes, both of them. So in essence, this is a pretty good Diels-Alder reaction because you have an electron rich diene and electron poor dienophile. It's also done at reflux, which basically just means you're going to boil these in some solvent. If these are solids, I'm not sure, but the point is this is done at high temperature, again, to promote the reaction. So that's another clue that this is a Diels-Alder because we're doing this at reflux or very high temperature. So again, diene, dienophile plus reflux, that is a clear indicator that this is most likely a Diels-Alder reaction. So if that's the case, we need to draw our molecules in such a way that it'll appear like a Diels-Alder is going to occur. So what I mean is, instead of drawing this in this kind of trans orientation here, we need to draw it more like it's a part of a cyclohexene, because we know that's going to be one of our products. So that is what that looks like, but now we have to make sure we include our methyl groups. So at 2 and 3, there are methyl groups, so that is these positions here. Those are 2 and 3. And then the dienophile has 2 substituents as well, but again, we know we're forming a cyclohexene, so we need the alkene part to be vertical like this, and then we can see this is trans because we have the aldehyde going up on one side and the aldehyde going down on the other side relative to the alkene, the double bond. So it doesn't matter which one you draw first. So let's draw it out like this to start. Right, so now the mechanism basically it's a concerted mechanism. So when we draw arrows, it's not really how the mechanism actually works because it is much more involved on the orbital overlap, but this is definitely what is used to illustrate this, and it's simply that you form this bond, you're forming this carbon-carbon sigma bond, and then you are forming this carbon-carbon pi bond and reforming the carbon sigma bond there to form the cyclohexene. So if we consider all of these stepwise, we're creating a carbon-carbon bond here, carbon-carbon bond here, that in essence creates the cyclohexene, right? Because here is, let me get a different color, call this 1, 2, 3, 4, 5, and 6. So at 1, we created a bond between 1 and 6. And 2 and 3 remained intact, and 4 and 5 we created a new bond. Right? So now The thing we're missing so far is we created a pi bond between 2 and 3. That is this second arrow here. Okay, now we have to consider our substituents. So at 2 and 3, we have methyl groups. We don't have to worry about any stereochemistry here because it's a part of the alkene, so it is there no chirality at those positions, no R or S. And if we look then at 6 and 5, we are going to have chirality at those positions. To illustrate the stereochemistry best, models should be used, but the general takeaway from using the models is that if you have an approach where the substituent is out like this or facing away from the dienophile, that is an exo approach. And whenever you have an exo approach, that always creates a wedge in your product. So since this is going away, this is coming out of the plane here. So a dash, or a wedge, excuse me. And now this is coming in, so we go into the plane. That is endo approach. That gives us this. So again, what this shows is that the trans orientation of the dienophile is retained in the product. But you may be wondering, why does this approach matter? Why couldn't it be, the other way? So what I mean is, why couldn't the aldehyde be like this? Right, and then I'll redraw the diene because that is unchanged. And there's no preference. There's no preference for one of these over the other. You will get both approaches because they're both going to be this trans, but now you're going to get different molecules in terms of the three-dimensionality. So if I draw this product now, this is going to be an endo approach on the inside and an exo approach on the outside. So we'll get this type of orientation. Now, if you compare these two, they're enantiomers. So actually what you're getting here is a racemic mixture of both of these, a 50-50 mixture of these two products, because there's no preference on the dienophile's approach. So because of that, you'll get 50-50 mixtures of either approach, which then gives you the racemic mixture, and this would be your product. It's very important to include racemic because if you didn't, you would assume that there's a difference in the approach, like the stability of that approach. So keep this in mind. All right, here we have another question. So once again, you're looking for characteristics of what type of reaction this is going to be. And first thing we can point out is we have a diene. Again, we just have two alkenes, two pi bonds in one of our molecules. And then this is clearly a dienophile because it is very electron poor. We know it's electron poor because of these electron withdrawing substituents that are adjacent to it. And lastly, it's done at reflux, again, high temperatures. This is all suggestive of a Diels-Alder type mechanism. All right, so then, just like before, we have to draw our diene in a way that is useful for forming a cyclohexene, which we know is a product of a Diels-Alder. So we draw it like this. And then we need to draw our dienophile also in a way that is useful for making a cyclohexene, which again is one of our products. All right, so there we get that. Again, just count your atoms here, 1, 2, 3, 4, 5. So that would be this position, 1, 2, 3, 4, 5. We get the exact same connectivity. We have this, the anhydride, the two carbonyls are across from each other with the single bond oxygen in the middle. So this is definitely the same molecule. It's just drawn in a different orientation to aid in our mechanism here. So now, just like before, this will approach the dienophile, form that sigma bond of the cyclohexene. We're going to form our pi bond here in the middle here between carbons 2 and 3. Again, should number these to be consistent. So 1, 2, 3, and 4. We get this type, and then this will be 5 and 6, which is these two positions here, 5 and 6. So what this is showing is carbon 1 and 6 are forming a sigma bond, 2 and 3, there's a pi bond, and then between 4 and 5, another sigma bond. So we draw all of that. Here's our 1 and 6 bond, 4 and 5 bond, and then there's a pi bond between 2 and 3. All right, so carbon 1, 2, 3, and 4, and this is 5 and 6 from the dienophile. Now, that is everything except for the second cyclic structure. Our dienophile here happened to be cyclic, which can be very intimidating and appear to complicate this whole thing very much, but it doesn't really, because all it's doing is now what's bound to 6 and 5 are connected together. So 6, we have this retained structure. Right, but now the question is that chiral? Are there any chiral centers? And you'll find that carbon 5 and 6 are in fact chiral, because what we see is 4 different groups, right? We have the hydrogen that's not drawn, that's implied at both of them, and then the carbonyl, the other fused part of the ring, this carbon down here at 5, and then carbon number 1. You can make the same argument or same assessment at carbon 5. So the important thing to consider here is those are chiral, so they have to have a chirality that we show, like a dash or a wedge. So the way this is explicitly drawn, this would be an exo approach, and we would have to show that the molecule they're both dashed, right? The substituents are both dashed. So let's start with that. And in this particular case, it's not going to be critical. I'll explain why. Right, so that shows the product as the mechanism is drawn here. But could it approach from the other direction? Right, like this. Just like we looked at in the previous example. Is there any reason that it can't do this? And this kind of appears like there's a lot of sterics here, right? Because this molecule, this part of the molecule is kind of in the way as you're trying to get your dienophile approaching the diene. And you'd be correct, except that you have to remember that this is a 3-dimensional structure. So this can actually like be contorted a little bit out of the plane such that that sterics isn't felt as strongly. And then you could get this approach. So this approach is feasible. And what this would yield is the exact same constitutional structure, so all exact same connectivity, but the 3-dimensionality is different. So the question is, which one is the right product? Well, these are both achiral because it's meso, right? So let's take a look at that. So we have this internal plane of symmetry here in both cases. Right, so what this implies then is the chirality in a sense cancels each other's out and makes this such that it's meso and then therefore it's achiral for both of these. So you can draw either one really because they're both achiral and there's not going to be a detectable difference between either of these 2 representations. They're going to have the exact same like boiling point, exact same features that you can detect. There's not even going to be a difference in the way they rotate plane polarized light. So because again, they're achiral. So in that case, you could draw either one and it would be correct. So this is all I had for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic suggestion or any questions, please feel free to leave them in the comment section down below and I'll get to them as soon as possible. But with that, I hope you all have a great day and I'll see you in the next video.